Hi, everyone. My name is Marieke, and this summer I will be graduating from the University of Oxford with a PhD in mathematical physics. So what I do is called theoretical high energy physics, and what we're concerned about is the fundamental constituents of nature and their interactions. So basically, the question we want to get to the bottom of is, how does nature really work? And this is an old question, and what I work in is an ancient branch of physics, which means that we actually already have some really good answers to this question. And many of these answers are based on the concept of perturbation theory. And perturbation theory is the notion that when we're studying some physical system, we can find a small parameter in this system and use that to take our equations and expand our equations in this small parameter. In this way, we can obtain simpler equations that are easier to study and to solve. So in high energy physics, this small parameter will usually be the coupling constant. And the coupling constant sets the strength of the interactions between particles. So what we'll do is we'll assume that the coupling constant is weak so that the particles don't really exert that much force on one another. The problem is, though, that as you might expect, it's not always true that there exists such a small parameter in the physical system that we're trying to study. So in particular, we could be studying some quantum field theory, and the coupling is in fact really large, and we say that we have a strongly coupled quantum field theory. So these strongly coupled quantum field theories actually render perturbation theory utterly useless. And the problem there is that makes these sectors of quantum field theory extremely difficult to access and study. So they may be hiding new physical phenomena that we can't actually get to with these conventional methods. And therefore, my research is precisely about finding fundamentally new approaches to be able to actually make a dent in these problems, using some sharper and more modern tools to study these strongly coupled sectors of quantum field theory.
Hi, my name is Ian Griffiths, and I'm a professor of industrial mathematics. I'd like to introduce here some work that we've been doing on predicting the spread of COVID-19. As we learn to live with this virus, it's clear that we need strategies in place to ensure that we stay as safe as possible while also continuing to live our lives. One aspect of this involves making sure that the rooms and environments that we occupy fall within safe tolerances. For instance, we might need to stay in a doctor's waiting room for 30 minutes, wearing a mask, or we might want to attend a fitness class for an hour, unmasked. We might want to dine with a friend. And of course, pupils need to stay in a safe space where they can learn. Now, we found that there are two ways in which the spread of COVID-19 is modelled. One way is by using computational fluid mechanics software. Here, all of the complex airflow patterns in a room are captured. This has the advantage of being able to predict the viral transmission accurately, but the downside is this takes far too long to make a prediction. By the time we know the safety level of a room, we've already been and gone from our fitness class. Now, the second method for predicting the spread of COVID-19 is by assuming that the virus is spread uniformly throughout the room. Obviously, this is a huge simplification, but it allows for rapid predictions for room safety. Now, we recognise that there was a great need for a mathematical model that bridges this gap to provide something that is complex enough to give an accurate prediction of the risk of catching COVID-19 in different places in a room, but simple enough to allow a rapid prediction to be made. Our new model is able to predict the risk in all positions in a room location for given ventilation settings in just 1 or 2 minutes. So this allows us to rapidly assess and thus offer guidance on the ventilation that is necessary to ensure that a room falls within the risk tolerances. We've worked on this project with the Welsh Government throughout the pandemic, offering advice as we developed our mathematical model. And we're now working to assess the benefits of placing COVID-19 air purifiers in a room and determining strategies for their optimal placement. I hope that you enjoy reading about our work in our case study and in the journal article.
Hi, I'm Ross. I'm a third-year PhD student in the CDT of Mathematics of Random Systems. Currently, I'm doing some research in the Navier-Stokes equation, we want to use some tools from stochastic analysis to study this equation. So Navier-Stokes equation is a very important PDE, not just in fluid dynamics, but also in mathematics. It has many applications. For example, if we want to describe the motion of some river or describe the airflow around some jet, we need to use Navier-Stokes equation. And Navier-Stokes equation itself is a very difficult PDE because it is highly nonlinear. And there remains some important and unsolved questions about Navier-Stokes equation on the solutions, existence, and smoothness. So our approach is as follows. So we look at some flow, we want to predict its dynamics in the future. So we look at some flow, we know that it has some velocity field. And based on this velocity field, we can calculate its so-called vorticity field. Basically, vorticity describes how what is the spinning behavior of this flow. And from a mathematical point of view, these two fields are equivalent. We can get the velocity from the vorticity. So we look at some flow and we suppose that the initial vorticity is kind of concentrated around some points, around some particles. And then we use this vorticity to approximate the velocity field, thereby determining the dynamics of these particles. And that gives us kind of like the structure of the differential equation here. And we need to add the Brownian motion to compensate for the diffusion term in the Navier-Stokes equation. So that gives us a SDE. And based on our approach, the simulation results are quite satisfactory. And we hope our research will shed some light in the study of this field.
Hello, my name is Solveig. I am a fourth year DPhil student. My research focuses on mathematical modelling of a disease called autoimmune myocarditis, which is inflammation of cardiac muscle tissue. Particularly, we're interested in how this disease develops as a side effect of immune checkpoint inhibitors, which is a particular class of cancer therapies. What we're really trying to get out of this research is two separate things. So one, we're really trying to better understand the immunology behind this disease, such that we can work towards prevention of it as a side effect of drugs. And secondly, we're trying to really make a case for a more holistic approach to cancer therapy modelling, where we don't just consider how a treatment affects the tumour, but also how it affects the rest of the body. This way, we can use mathematical modelling to make cancer therapy both more effective and safer.
Hi everyone, my name is Jagoda Kaszowska-Mojsa, and I'm a Skłodowska Research Fellow at the Mathematical Institute at the University of Oxford. Have you ever wondered whether we should freeze an economy in order to slow down the pace of coronavirus transmission? Or have you ever thought about what the scale and composition of an efficient lockdown policy should look like? I'm sure that you have also wondered whether social distancing and lockdowns were still necessary after the introduction of vaccines. Thanks to the funding from the European Union Horizon 2020 Research and Innovation Programme, we are able to answer these questions. Our first paper, To Freeze or Not to Freeze, Epidemic Prevention and Control in the DSG Model using an Agent-Based Epidemic Component, was published in 2020. In this paper, we showed that we would have been better off if, rather than following a gradual lockdown strategy, cyclical abrupt lockdowns had been implemented. And this observation is of major importance, as it is in contrast to the widespread belief that we should keep an economy at least partially open for as long as possible. After the introduction of vaccines, we ask ourselves whether this conclusion about lockdown strategies is still valid. In our second paper, Immunity in the APM-DSG Framework for Preventing and Controlling Epidemics, Validation of Results, we proved that cyclical lockdowns may still be necessary even if we gain immunity after the recovery and vaccines. I hope that you will find these papers interesting. Stay safe.